So thank you very much, everyone, for coming. We're now a couple of minutes past the hour, so I think we'll get started because we have a lot to get through today. In today's exciting webinar, I'm really looking forward to it on enabling painless reuse of shared research data and code, a case study on computational reproducibility. My name is Jennifer Abel, and I am the new training coordinator here with the Portage Network. It's nice to see some familiar faces and also to see some new faces, and I look forward to working with you all over the next few months. Before we get started, I'd like to begin by acknowledging that the land which I'm speaking to you from is the traditional, ancestral, and unceded territory of the Coast Salish peoples, including the territories of the Musqueam, the Squamish, and the Tsleil-Waututh nations. And if you know where they are, then you know where I'm talking to you from. So today's webinar is on data reuse and computational reproducibility, which have become increasingly important in scientific work over the past decade. This webinar consists of two talks, each providing a different perspective on computational reproducibility. The first talk, by Anna Trisovic, will focus on advancing and assessing the reproducibility of data and code deposited on a Dataverse data repository. The speaker will present a large-scale study of rerunning preserved code. Following the study outcomes, the speaker will present lessons and how to alleviate the observed lack of reproducibility. Also, she will give a refined approach for research dissemination for painless reuse and ideas on how to signal quality in shared research. The second topic by Qian Zhang will share challenges and opportunities associated with research data and software management in support of the high-performance computing-driven computational reproducibility of research. The speaker will then summarize lessons learned and good practices for facilitating reproducible research. A few housekeeping before we get started. You've been muted automatically when you entered the room. Know that this webinar is being recorded and the chat may be archived for those who aren't able to attend. We encourage you to use the latest version of Zoom so that you have access to all of the features, including security updates. Please feel free to use the chat feature if you are having technical difficulties or have additional resources to share. But if you have questions to ask the presenters, please use the Q&A option. We'll answer questions at the end, and you may also raise your hand if you have a question. Questions may be asked in English or French. They will be answered in this webinar in English. You can find the complete code of conduct for Carl, under whose umbrella we work, at the address listed below. I'll pop that in the chat as well. Carl and the Portage Network are committed to providing a welcoming, safe, and harassment-free environment for its staff, membership committees, and working groups, as well as for participants, speakers, and organizers of Carl meetings and events. We do not tolerate harassment of any kind. Our presenters today are Anna Trisovic, who is a Sloan Postdoctoral Fellow at the Institute for Quantitative Social Science. Her research focuses on computational reproducibility, data provenance, and open science. She investigates how data repositories can facilitate reproducibility and what are the most common causes of research irreproducibility in depositive research. In these projects, she collaborates with Merce Crosas and the Dataverse team. Previously, she was a postdoctoral fellow at the University of Chicago, where she worked with the Energy Policy Institute and the library. She completed her PhD at the University of Cambridge in 2018 on the topic of data preservation and reproducibility at the LHCb experiment at CERN. While at CERN, she worked with the LHCb collaboration, CERN Open Data, and CERN Analysis Preservation Groups. During her PhD, she was a scholar of the Muir-Wood Studentship of Newnham College, the CERN Doctoral Student Program, and the Google Anita Borg Memorial Scholarship. And Qian Zhang is the 2018 CLIR Postdoctoral Fellow in Software Curation at the University of Waterloo, co-hosted by the University Library and the David R. Cheriton School of Computer Science. Her responsibilities include leading research into both data and software curation. In specific, Qian actively builds collaborative working relationships within the library and with faculty and research teams at the University of Waterloo to establish a framework and a set of best practices for curating data and software code that requires preservation over time, primarily for their value in facilitating research and the reproducibility of research. Before joining the University of Waterloo, she worked as a postdoc across the RDS, Research Data Service, of the Library, iSchool, and NCSA, the National Center for Supercomputing Applications, at the University of Illinois at Urbana-Champaign. So with your introductions to these people, I'm going to hand it over to Anna, who's going to do the first talk. And Anna, you have the floor.
Thank you so much, Jen, and thank you for the nice introduction. Can you hear me well?
Yes, we can hear you.
Okay, so I will now share my screen. And yeah. Okay, so now you should see just the slide and nothing else. Is that correct?
That is correct.
Yes, we can.
Okay. sorry, but just yeah, better safe than sorry. Okay, so yeah, thank you so much for the introduction, and yeah, thank you everyone for joining me today. It's really nice to present and to be here. So yes, as Jen said, we are going to have 2 talks today. So after this short introduction, now it's like a little bit longer. We will have 2 talks. So I will give a talk, and then Ken, and then at the end we will have also answers and questions. We will be happy to answer your questions, but also we will have a few questions for the audience. Okay, so just before we start, I would like to acknowledge everyone, all the people and organizations that fund and support our research, and these are clear. And thank you, of course, to Portage for organizing this seminar, and the Sloan Foundation, and AWS, where I've done my large-scale study, IQSS, and of course the computer department and library at the University of Waterloo. Okay, so this is kind of like the first slide of my presentation. I'm going to talk about the problems that we see in reproducibility and how we can alleviate them. And what exactly is going to be my talk about? So first, I'm going to have an introduction. I'm going to tell a little bit about the terminology that we use, what means what, and also I'm going to tell what Dataverse is, and how we can enable quality of this shared data and code, and how can we ensure it, how can we signal it. Then after that, I'm going to show you the experiments that I've run. So these like large-scale experiments in AWS. And in particular, what happens when we automatically re-execute a large number of these replication packages, and what are the most common errors that we see. So at the end, we are going to try to have some conclude with some lessons learned, and how to actually proceed, how to alleviate the situation, and have painless reproducibility and reuse. Okay. Okay, my slide is not, oh no. Right, okay, just one more thing. My internet is not stable, so in case I disconnect, I will be back. But yeah, that's important for you guys to know. So, introduction, what does it mean? What is reproducibility and what is replicability? So, it was a great news that last year we had a book that actually defined all these terms, and it kind of put an end to all this discussion, what people see as reproducibility and replicability. So I'm going to cite their definitions. And in particular, reproducibility is obtaining consistent results. It's an ability to obtain consistent results using the same input data and code and computational steps. Replicability is obtaining consistent results across studies that use different data sets. So in particular, if I observe one phenomena in one experiment, I would expect that other people are also able to observe this phenomena in different kind of experiments in order for this result to be replicable. Whereas reproducibility, a person would take my data and code and rerunning everything, and by rerunning everything is able to get the same results. So how does this look in practice, and how does this research process goes? So first step of research is, of course, we have a research question, and we collect data, and maybe we buy data, or we generate data. And conduct the data analysis, find the best methodology, and so on to conduct the data analysis, and then process this data and then interpret the results. After this part is done, typically researchers publish their findings through a journal publication. And after that, it is important that these data sets still stay active, potentially accessible, if that's possible, and preserved. So they can disseminate this data and code through typically data repositories. And in some journals, this is actually a requirement. However, researchers typically face a lot of problems when disseminating data and when needing to actually document their data and code, because there is a lack of guidance for different fields. So this kind of lack of guidance actually later hinders reproducibility and reuse. Okay. Okay, I'm in a constant fear that I'm losing connection and that I'm unable to go through slides. Okay, sorry. Okay, so as I said, one of the typical venues to publish, to disseminate data and code are data repositories. And Dataverse is one of these data repositories. It is a free and open source software platform to archive, share, and cite research data. So Dataverse is a software platform, and there are many Dataverse repository sites around the world. So I think currently there are 60 around the world, and you can here see on the map on the right-hand side where they are. Yeah, and these 60 institutes that have Dataverse instances, they're used by one or more institutions or labs. Okay, next slide. Okay, I see I should have downloaded these slides. So here we can see how actually a data set, how Dataverse looks like, what is a landing page. So here the Journal of Political Analysis has its own collection on Dataverse. And here we can see that in the corners are replication data for one of the studies. And similarly, other journals have their own collection. So here is American Journal of Political Sciences, where they have their own interface and landing page for their replication data. So now you might say like, oh wait, this is replication data. And previously we defined replication as something a little bit different. This should be reproducibility, but it is also important to note that Dataverse is a little bit of an old software, so still uses this a little bit different terminology than what I defined a little bit earlier. So in practice, this should be reproducibility data sets. Okay, and in addition to these collections by different journals, there is also a high-level Dataverses that does not belong to any journals. Okay, so quality. How do we ensure quality in disseminated research data and code? How do we ensure quality in Dataverse, and how do we signal it? So data quality is determined by its fitness for use for a given community. So of course, every community values accuracy, precision, consistency, and completeness of data sets. However, in order to enable reuse, we need to document these data sets very well. So that means that before data sets are published and disseminated, there is a high potential to either enhance its future reuse or essentially diminish it if we don't do it very well. So after the data sets are deposited, a way in which data repositories can signal data sets is, for example, through a number of views, a number of downloads or citations, even though this is not a definite measure whether a data set is of quality or not. There could be also other reasons why people want to view or download or reuse this data set. Okay, so when it comes to computational metrics and computational completeness, in order for the data set to be reproducible and for the results to be reproducible, the necessary components are, so input data, research code, and code dependencies, so libraries, system dependencies, and so on. So research workflow is also important. So we know the sequence of steps, what should be run first, what second, what third, and so on. Other things like computational infrastructure, a lot we will hear from Kian about all the problems that we had when trying to re-execute something on a supercomputer, for example, but also contextual information are important, and all these things that researchers routinely agree on and routinely use their common sense, but are often never documented in data repositories. So here, in contrast of all these necessary components, we can see how actually how is data set actually deposited. So we can see a bundle of these like do files, which are data files. We can see data sets, these are like tab files, and we can see also some PDFs that serve to inform us how to use this data set. But is this the right way to preserve data and code, to disseminate it and to enable reproducibility? So we will see that a little bit later, but I think you're probably thinking that you probably already know that this is not the way to actually enable computational reproducibility in the completely. Okay, so now I'm going to tell you about the experiment that I was doing on AWS. So Dataverse, in particular Harvard Dataverse, has a very rich collection of many data sets and also a lot of code with these data sets. So the idea is, can we re-execute these like data sets out of the box? What will be the biggest problems that we face? So before I start, so when I say a data set, actually I mean this bundle of data and code and descriptive metadata. So the bundle of these components that people actually share on Dataverse. Yeah, and you can see the picture on the right-hand side. So because Harvard Dataverse has a rich collection of these data and code in of R, containing R code, we decided to test this approach for R. So in particular, okay, so allocated time to rerun each R file is 1 hour. Though we also ran experiments with like 10 minutes per R file or some other time. And we studied over 2,000 data sets containing over 8,000 R files. And all of this was done on AWS. I don't have on AWS batch. So I don't have like complete description how everything is done in this presentation, because I would like rather to go through the results and what they mean to us. But if anyone is interested to find out more, I would be happy to also share. So what do we find out when we look in all of these more than 2,000 data sets? So these bundles of data and code. What is a typical size? So we see that, so this is how the distribution of dataset sizes look like. Most of them are less than 10 megabytes. Most of them are even less than around 5 megabytes. That kind of shows us this like long tail of science, that actually most of the studies and most of the research is done on small data sets. Yeah, using kind of like small studies, small data sets. Yeah, okay. Then what else can we find out of these data sets in general? So distribution of number of files. How many files we have in a data set? Is just like one data file, one code file, one documentation file, or there is like many files? Turns out there are many files, often less than 20, but yeah, more than 10 in most, well, okay, less than 10 in most cases. And these are not all possible datasets on Dataverse, but only the ones that contain our code. Let's see, next. Okay, I'm waiting for the slide to, okay. Okay, so what is a distribution of average file name lengths? So we can see that average distribution is around 10 to 20 characters. Why is this important? It is important because the longer file length is, the more information we have on what is inside that file, right? So the more descriptive it is, the more reusable it is, the more we know what's happening in that. If it is just called like, I don't know, a.text or temp.text, that's not enough for us to have a description. So it kind of like also tells us, it serves as some sort of documentation. But here on the right-hand side, we see how many of these replication datasets or replication packages, these are the same thing, contain independent documentation. So either a README file or an instructions file or a code book. So these are good news. Most of them do contain that. So around 60% of the replication datasets contain README or instructions file. Okay, so now some exciting results. What happens when we try to re-execute all these R files? But bear in mind, we are re-executing all these R files automatically. So we don't really, we are not able to see exactly what's happening on them. We just know whether it executes or it throws an error. And these results are not super encouraging. We see that with R 3.6, most of the files immediately crash using the Anaconda R environment that is already quite rich in the libraries that it offers. So then we decided to implement some code cleaning and see, can we improve these results? Why so many files crash so fast? Can we improve this? And voila, something happens. We have improvement of around 10% of the cases. So we see that these files either successfully re-executed or there is a time limit exceeded. So in these files, each file is given 1 hour to run. So if it successfully runs within 1 hour, then it's a success. If it crashes, then it will immediately notice the crash. And then time limit exceeded is if it actually needs more time to run over this 1 hour limit. So what were the errors? What were the main problems? So without code cleaning, we see that library error is really dominant, and it appeared in 60% of the cases, if not more. Then another typical error is this set working directorium, which is typical thing for R. So it is actually considered to be a good practice in R to immediately set a working directorium, essentially. And because people often put fixed paths or absolute paths, these things very often crash once the code is, once there is a need for the code to be portable, once someone else needs to re-execute it on another environment. Then we did also notice this like time limit exceeded. I actually rounded it to 1%. It was less than 1%. And then there were a lot of problems with files. So in 10% of the cases, they were like either missing a file or so on. And then also we have other errors. With code cleaning, we really see an improvement in the libraries. So from 60%, now libraries crash 25% of the times. And that is because our programming language is actually not backward compatible. So for the things that work with this version of R, did not work for the other versions of R. which means that in this 25%, maybe the R programming language would be older or newer, or simply this like library could not have been installed. Set working directorium, it actually shows less than 0%, I mean, maybe 0.1 or 2. And that is kind of like the thing that we targeted with code cleaning. So we immediately, we looked for this like specific function and tried to like delete it or update it. Time limit exceeded. Now when the code actually runs, we see this around 50% of the cases, and file errors are of course present still because people often forget to maybe add all of the files, or there is other problem. And we see that around 10% of the cases. There is also a huge variety of errors that appears in other 50% of the cases. For example, some of these are, for example, RStudio errors, and yeah, and so on. Okay, let's see if I can go to the next slide. Okay, it's a little bit slow. Okay, so this plot shows us the re-execution rates per year of publishing. So per year of publishing data and code in Dataverse. And here we can see what I was hinting before, and that is that R is not backward compatible. So we see, because we use the newer version of R, we can see higher reproducibility rates in the last few years than we can see in the further in the past. However, just one caveat, this is a little bit, these like conditions are a little bit different than in the previous study. So here actually, when I was re-executing these files, they didn't have 1 hour allocated per file. They actually had 1 hour allocated per replication package. So it's a little bit different conditions of the analysis, but the analysis is still the same. And we can really see this interesting plot, so I thought that it was worth showing it. Also, what we can see in the same conditions of the analysis, so not the full hour per file, but the full hour per whole replication package, is that we can see that journals that have curation services, like American Journal of Political Sciences, that I showed in the beginning, they actually have higher re-execution rates than some of the other journals that don't have this these services. So yeah, I thought that was also interesting to show. Okay, so what are the next steps for this analysis? So we are currently analyzing, we're doing this study for 3 different versions of R, trying to kind of match different points in time and see what is the sensitivity in between the re-execution and the version of R. So we also rerun this study with different things in code cleaning, and also different times allocated per each file. And we are preparing a manuscript, so hopefully you will be able to find everything in detail on this study in an article. Also, when it comes to Dataverse, our next step is that we want to avoid these common execution mistakes. So we are considering implementing something like automatic continuous integration when the data and code is being deposited, so that we can immediately see what are these errors, if we have these errors, and we can try to prevent them. So in case this this seems interesting to you, or you're working on something like this, we would be happy to get in touch and maybe brainstorm together on this problem. Okay, so one more study, like along the same lines. So once we had like a working pipeline, so once, how does it go? when we have a hammer, everything looks like a nail, but okay, it's not really. So we had a pipeline that was working, and I was wondering what happens if I put Python code in this pipeline. And here are the re-execution rates for Python files for Python 2.7 and Python 3.5. Again, we were using Anaconda environment. And here we can see that, well, it's not very different. And also, yeah, it's important to say that this is both with code cleaning. So in a sense, I scan all the code files looking for the libraries that were used, and I pre-install the libraries before trying to re-execute the files. So there are only less than 400 files in total on Dataverse Python files. So there is like it's not like such a huge volume of files, but again, this is what we see when we re-execute the files. And most common errors that we see are import errors, again signaling that there is a difference in between Python 2.7 and 3.5, and syntax errors. And it is really interesting to see, I mean, of course, very much expected to see in Python 3.5 how it is really complaining about this like print functions that is looking for brackets. So that is kind of like the type of mistakes that we were looking at both of these environments. So also what else we learned about packages that contain Python code is do they contain documentation? And in most cases, they actually do contain documentation. So around 70% of the datasets with Python code contains some sort of documentation. It's either a README or a codebook or instructions file. And also, so Python, the language Python has these kind of environment preserving files, such as requirements.txt or environments.yaml. And I was wondering whether we can see these files in Dataverse, and because that's kind of like part of the training with Python, that one should be aware of these different environments and can always capture them in these files. And interestingly, we see that there are no datasets out of 92 datasets. There are no datasets that contain environment.yaml, and there is only 6 that contain requirements.txt. And yeah, and then if this file was present, the kind of logic in this experiment was to try to install these libraries in the requirements. Okay, so now a little bit the conclusion. So what we learned from this. So in principle, we see that the way how things are shared right now is not the best way. And there is container technology or encapsulation that provides a way to share data and code in such a way that it is actually portable and re-executable. It is often used on the cloud for like fast deploying of the applications. And yeah, it's also becoming more popular now in science and academia. Containers are popular for preserving code and portability and reusability. And they are one of the best solutions we have for reproducibility. And yeah, in addition to maybe virtual machines. Okay, so there are different types of containers. Some of them are better to be used for like personal computers. Some of them are actually geared toward the supercomputers and HPC. So they do present a variety there is a variety in how we can enable computational reproducibility. So what does that mean for Dataverse? How can Dataverse seamlessly try to implement this encapsulation technology and enable reproducibility? So there are other projects called, for example, here, CodeOcean, Wholetail, Ranku, ReproZip, that do use containers behind the scenes. And they capture both these computational environments that can be shared, reproduced, and reused. So the idea is okay, so here we compare them. So on one hand side, we have reproducibility platforms that enable, okay, so reproducibility platforms are essentially these projects like CodeOcean, Wholetail, and so on. And they enable portability and reproducibility because they use container technology behind the scenes. However, there are still benefits in using data repositories, and that's in particular findability of research data and code, and citation, and long-term accessibility and preservation. And so the idea that Dataverse is kind of going for is the integration of these two different approaches. Okay. Oh my God. Okay, so the integration means that, so code, encapsulated data and code are encapsulated in Wholetail, and then they're sent to Dataverse for preservation and dissemination. And this way, all the necessary components, such as environment, are kept in Dataverse. Yeah. And then the user is able to actually see all these environments, encapsulated data and code with all the environment metadata and information, and so it's easier, so that it is easier for these things to be reused. Okay, I'm aware that I'm actually over time, so that's why I'm like a little bit in a panic right now. Okay, so Outlook, how can we enable painless reuse of shared research data and code? So as I said, we need to avoid common mistakes, and that's best done if we try to like re-execute our data and code in a clean environment and see what happens and what additional things we can capture. So virtual containers and general virtual environments are the best thing we can to use to enable reproducibility, and we should definitely include them in sharing data and code. And yeah, finally, another thing is if we have better metadata to capture these things and the computing infrastructure, we will immediately know what infrastructure to use, and that will be very helpful for reproducibility and reuse. Okay, I'm very sorry for being a little bit over time. Okay, I guess Kian, the floor is yours now.
Thanks, Anna. Let me share my screen. Yeah. Hi, everyone. Are you able to see my screen?
Yes, we can see you.
Okay, thank you. So, thank you, everyone. I'm Chen. So my talk is about enabling the painless reuse of shared research data and code for the high-performance computing-driven computational reproducibility of research. A quick overview of my talk is I'm going to talk about why is the HPC-driven reproducibility important, what it is, and more basically, what is the HPC-driven computational research. And then I will use a case study to demonstrate the challenges and opportunities of the HPC computational reproducibility, and then give some practices that we have used for this painless HPC-driven research reproducibility and reuse, and give an outlook beyond that. Traditionally, there are two, or the two branches of the scientific method. The first one is a theoretical method based on the deductive mathematics and some logics, some formal logic. The second branch is the experimental or the statistic analysis of controlled experiments. So the computational method is what usually people call the fourth paradigm of research method. Basically, when we talk about the large-scale simulations or the big data-driven computational science. And especially for the HPC-driven computational research is not only they cover the huge amounts of data set, but also including the computational power of high performance computing which is an application of the supercomputers as a practice for aggregating the computing powers in a way to solve the computational problem that are either too large for standard computers to solve or would take very long time to complete. And the third part of the HPC computational research is it will involve most of numerical models, and depending software and packages are essentially code. So software is persuasive in the modern digital research landscape, with data and publications being created, analyzed, and stored electronically, and the associated tools and methods expressed in the software. So research software is essential to progress in almost all research fields, especially in the scientific research, which is dependent on the quality and accessibility of the research software at all levels. That is why it is now critical to address the new challenges related to the development, deployment, and long-term maintenance of the reusable research software. Similar to the traditional computational reproducibility introduced by Anna earlier, so the HPC-driven computational reproducibility is also about obtaining the same computational results or the outputs using the original author's own artifacts by conducting some research, and but it's usually done by a different team, and using the same, for example, the same experimental setup, including the same artifacts, the data, the code, the same measurement procedures. But the little bit difference here is that we may choose to use the same or different operating conditions based on the availability of the HPC resources that have been used for the publication in the original paper. Way is we do the the computational reproducibility, or specifically the HPC-driven reproducibility. So reproducibility is a process, not an achievement. This is a statement in my paper, most recent paper for the European Conference in Information Retrieval, focusing on the replicability of the information retrieval reproducibility experiments. From there, through a concrete case study of 7 open source, the IR usually here is the information retrieval system that were reproducible 4 years ago, back in 2015. Our paper espouses a view of reproducibility in the computational science as a process, but not just a point-in-time achievement. And moreover, the main purpose of the reproducibility is to verify the scientific method and root out errors. This is why the main reason, the research papers were first published, and then data was passed around the community for those who are interested in or who are active in the science. More importantly, a lot of scholars are not sure about what they are going to share or when they are going to share them. However, the concept of reproducibility helps to make this clear and also help us to frame an agenda for digital curation. In this way, the scientific communication and access are augmented at an internet scale. Also, it's also worth mentioning that the data reuse stage in the overall research data management lifecycle, as well as complaint with the data fair principles. Right now there's no well-developed community practices existing on the computational reproducibility topic yet. So there is a huge potential for the data professionals, library the librarians, the community researchers to explore how to conquer this credibility crisis in the computational science by providing the guidelines and infrastructure and other resources regarding the reproducibility. Here I am showing a case study in the Astrophysics focusing on the HPC-driven computational reproducibility. This paper was published in 2015. The model it was used called the Illinois GRMHD. It was an open source, user-friendly GRMHD code for the dynamic spacetimes. And I need to mention that right now this numerical model has been successfully integrated into the more widely used community-based numerical model, the Einstein Toolkit. Most people know that in astrophysics field. So the Einstein Toolkit is a community-driven software platform for the computational tools to advance and support the research in gravitational waves and astrophysics in such areas. In order to start the reproducibility, we need to have access to some resources, for example, the data and code. In the paper back in 2015, at the footnote of the first page, it mentioned that instructions for downloading, compiling, and using the code could be found, with this link. However, this link was outdated for the past 5 years. It has been moved to a new places without, updates or notification to the broader audience. I was lucky to have the opportunity to, be able to contact with the original author, and he gave me, he told me the new link to the numerical model where it is located right now, and so I was able to have access to the code and some key parameter files for these numerical models. The simulation makes use of the HPC resources through the EXCEED program. EXCEED is short for Extreme Science and Discovery Environment. So the two computational clusters from the EXCEED ecosystems we have chosen to use are STEMPES 2 from the TACC from the University of UT Austin. And the other one is called COMET, which is also a cluster from the UC San Diego Supercomputer Center. So both clusters provide us as the reusers with a scratch space, or we call the file systems, for the temporary and large size simulation data storage that are produced by the numerical model. The general workflow of the reproducibility is starting with downloading in necessary data and code, especially for the numerical model. We do the compile the numerical model or the source code by doing some configurations and maybe some debugging. And then we customize, after the code was successfully compiled, we also customize the parameter file that is specific for our dedicated use case or simulation. And then we submit our jobs through the shell script to the queuing system, and then wait until the clusters finish the simulation, and then we do the post-simulation analysis and the visualization. Here I'm showing just the results of our reproducibility, the preliminary results of the reproducibility from this study. So because there are a lot of domain knowledge and details about the specific the paper, so I try to avoid that. Just showing that right now, I'm showing that I'm able to reproduce or able to execute the and reproduce almost the same results as we have in the paper back in 2015. So we call it was reproducible, but the specific the accuracy of our reproducible results, and that in the paper we still need more in-depth analysis. I need to mention that you know, because this figure on the left, the figure was published in the paper. So it's important when we do the reproducibility, it's important for us to not only to be able to execute the simulation and get the results, but also be able to have access to the dedicated data and analysis code for this, for creating this, this figure. So I will talk about this more in the next slide. So some observations and lessons we have learned. So is even though we have some, we are able to access to some resources like the data and code and documentation, still it's not complete. It's insufficient when we come to the real execution or the reproducibility activities. For example, as I mentioned earlier, we don't have access to the computational, we don't have access to the post-processing analysis scripts and the data associated to the figures in that in the previous slide. So there are two ways always associated to that. The first one is we try to contact the original author to request for such information. The second way is also not a smart way, is that we have to manually digitize the figure to get all the data points from that figure, and we try to compare those data points with our reproducibility results. So that's how it works. Another thing is that the computational, when we run into a lot of, you know, the errors when we try to compile the complicated numerical model, and also try to execute to run the executables. So some of the reason is because we cannot stop the regular maintenance of the clusters when they have to upgrade the software and hardware. So for example, if today I'm able to run the simulation successfully without any problem, but after the maintenance upgrade, then maybe the next day I will have trouble, you know, running exactly the same code one more time. So that is some issues we cannot, you know, avoid from. And also, as I mentioned earlier in the paper, so the link rot and also the software incompatibilities, you know, after these upgrades, and also when we are not accessible to the specific version of the software or the hardware infrastructure, we will run into such issues. And also sometimes there will be missing the key parameter information or the parameter, the values there. So for this reproducibility, we have to actually do this reverse engineering to guess or deduce what's the specific value in the parameter files to make sure that we can, you know, make a logical sense for the research reproducibility. And because those information are not able to be trackable from the perspectives of the original authors. So that was not good. So some other lessons we have concluded is that we ran into, for this complicated numerical models using the HPC resources, we have ran into the installation issues. So installation on the local laptops, we realized that unless it has to be from scratch and a clean slate, then we are able to compile and execute the simulation. If we are going to install the numerical model on the HPC cluster platforms, then we'll usually run into the setup issues. And so we think that we need more instructions on the installations, the documentations, and even a full list of the checklist, which parameters and specific parameter values we need to check. And also we ran into some issues when we submit the jobs to the different queuing system when moving from across different clusters. So at some point, we also need to provide more human readable information for this provenance tracking purposes. So based on those observations and lessons, we are aiming to develop a generic setup template to configure a new machine. Here, machine is the new cluster. So this includes the machine definitions, the option list with all the hardware infrastructure and software dependencies, everything, and also the submission script and the running script submitted to the queuing system. And right now, we are working on running all the reproducibility use cases on the exceed clusters, which are more than 2 clusters we are currently using. But also, we planning to also try to, interoperate these reproducibility moving from the US clusters to the Compute Canada or the Parameter Institute local clusters, or even the AWS for different attempts, and draw some conclusions on that, and to help the researchers, whoever want to, compile and download and work on and using these numerical models for reuse, not actually the reproducibility. Eventually, reuse is a higher level than the reproducibility. So exactly why the such HPC reproducibility and reuse is so difficult. So sometimes, we need to think about how accessible is the particular version of the model or the code. How specialized the platform needed is, for example, the particular hardware, the compilers and source code that is needed, and where and how was the simulation was run. And also for the model reusability, the setup thing is how easy for the software to be installed, compiled, and set up. And the human efforts is about the human hours required to spend on reproducing the specific scientific research. And for the data, the simulation inputs means that how much efforts for us to achieve, and acquire and manage all the inputs used for the simulation. The output usability is about how easy is it to use the outputs outside the original context. Does it adhere to any standards? What community standards or conventions have been used? And if the metadata is sufficient for others to understand the output without running the simulations, something like that. Other difficulties or obstacles is about accessibility. So, for example, the ability for the common software to read the data in the future, 5 years from now, 10 years from now. And the archive accessibility is how easy is it to access the data? How long will the technology be usable in terms of the data formats and the programming languages? So some data formats and programming languages might be badly used, or some of them are not in a proprietary formats. And the computational costs, about the economic cost, like when we talk about the ARC advanced research computing resources, the high performance computing, all these computational hours, how much do we need to pay for that? So the high computational cost could be produced with specified platforms, and it will cost a lot. For the storage cost is about the volume of the output that is actually generated by the model, or the simulation. So these are all the different considerations we need to think about. But also this also provides us a great opportunity, to help us to have the opportunity to ensure the transparency, the reproducibility, and the reusability of the research results by providing us the effective communication between the research outputs, the data publication, the code, and ARC resources, and how could these communications evolve to accelerate the public access while advancing the quality of scientific research. So promoting the enhanced access to the research outputs and resources will provide us opportunity to lead in the specific domains in enabling the accessibility of the knowledge, information, and data generated by federally funded research, and by increasing access to the software and code. This will in turn support research integrity, productivity, and efficiency. This includes the policies and strategies promoting the open access to research outputs, network and collaborative initiatives aiming to facilitate open access, the support for the research infrastructures, and again, the research software should be recognized as a primary output of research, not as secondary to the publication or data. The recognition of the role of the research software in research and the recognition of the research software as a reusable product and the funding for it will specifically, help us with, the sustainability and the reproducibility of the research itself. Some other opportunities is including to develop the standards for the reproducibility badges. So NISO has drafted this recommended practice for the reproducibility badging and definitions, and on August 20th this year, the Association of Computing Machinery has released new changes to the badging terminology by following and aligning with the NISO's recommendations on the reproducibility badging and definitions. Other than that, we also need the reproducibility also provides the opportunity for the develop tools for supporting computational science, including dissemination or reproducibility platforms like the Dataverse in the previous talk, and the workflow tracking systems, and also encourage the better documentations, and also encourages the best practice and guidelines in the research community or societies, and also provide more training opportunities, on the core data and code reuse expertise, and to disseminate to the broader researchers. Some good practices for the Painless HPC-driven research reproducibility and reuse include, for example, the accessioning, stabilizing, and evaluating and describing the digital objects, documenting and making the documentation available, sharing resources including primary and secondary data and associated documentation that have been collected and used in analysis, primary and secondary data outputs, results, and documentation produced by the analysis, software programs and documentation for computing, published results, and also the trying to the research software implementation details, is also needs more attention. So software and hardware dependencies for replicating published results, including technical details and the associated software systems and software environments, is also important, key factors for the feasibility of the reproducibilities. And also, other than that, we also need to try to make open data and open publication and open code, and provide access to most all necessary scholarly outputs that have been used in our research. The outlook is that the extensive reuse of data and code will become the norm. The researcher competitiveness in the science field can also be enhanced by increased access to the software and code to attain some productivity and efficiency benefits that will become possible when extensive reuse of software becomes the norm. So it's yeah. correlated, and achievement of this will require a significant cultural change supported by enabling the funder and publisher policy and processes, and also the author culture change themselves. The takeaways for the both talks here: the reproducibility is a process, not an achievement. The research community's recommendations on good practice will be a huge thrust for the best practices and also the feasibility of the computational reproducibility. We still need to pay attention to the greater clarity and guidance on dissemination of the computational claims, including data, code, the workflows, and the publications, make them coherent with each other. The code's dissemination in the data repository includes avoiding common mistakes by testing code in a clean environment, including the virtual environment in the shared code, better metadata to capture the complicated computational infrastructures. So here is the end of my talk. Thank you, everyone. And we are now open for the questions. And just a reminder, if you don't have many questions, we also have some questions for the audience. Thank you.
Thanks so much, John and Anna. We have had a few questions in the Q&A. We have one that is open right now, which I'll read out. This is from the ITO director. On the slide in Anna's talk that shows the errors observed with and without code cleaning, do I understand that the code cleaning introduced new other errors from 17% to 50%, and more TLE, time limit exceeded errors as well? Also, the two figures showing the errors in execution of Python 2.7 and 3.5 looked identical to me. Am I missing something?
Hi. Okay, so I answered it in the chat. So yeah, that. Okay, let me see. So
yeah, I have the slides here. So if you want to point to specific,
I hope you can. Yeah, I hope you can see me. I again see this message like your internet is unstable. Okay, so yes, so well, that's exactly kind of like what happens. So we have the first. It turns out that before we use code cleaning, we had one set of errors, and then after we use code cleaning, turns out that these errors, like solving these errors, only unmask more errors. So that's essentially what we see in the R analysis. In Python analysis, yes, it is true. These dots are the same. They shouldn't be. And this mistake only happened because they are actually also very similar in as they are. So I posted on the chat like the exact numbers. So in Python 2.7, we see that 93 files were executed instead of 83. So that's where this error was. So 93 should have been in this figure. And then for 3.5, that one is correct. So that one is that 89. So yeah, the difference is very small. That's how this error got propagated. So I'm sorry for that. But okay, I can also go through the other questions. So how hard was it to retrieve actually these data sets that contain both data and code? And that is, I think, a feature of Harvard Dataverse. So we were able to retrieve exactly this data sets that we wanted. So not necessarily not to go to maybe retrieve more that we needed. We did send through the API a query asking specifically for packages that contain either Python or R code. Okay, the second question was, Okay, so how does this analysis, how did the analysis go? So were there errors recorded before or after cleaning, or just the first error encountered? Yes, so we essentially had two different runs. In the first run, we had without code cleaning, and we would just try to re-execute the code and capture the first error that we see. So without really trying to see what's happening there. And then in the second run, that kind of happened completely independently of the first run, we first conducted code cleaning, and then again rerun the files and again capture the first error. And yeah, that is exactly what we most often see, is that the first set of errors kind of like just mask other errors that exist in the code. That's why this approach, where we try to re-execute code well out of the box or without computational environments, is really hard and would really present a time investment trying to understand what's happening and to reinstalling all the necessary dependencies. That's why my talk advocates for the use of encapsulation and containers to encapsulate these things. Okay, and then I had a last question. So were we able to compare to the previous results? So no, we didn't know what was supposed to be the outcome of the code, so we didn't compare with the previous results. Yeah, that's why this study might be a little bit well, naive maybe, because we couldn't compare with the results. But kind of like the strength of this study is that it is it's just the sheer numbers of the files that we were able to re-execute and test. So it's like I don't know, more than 8,000 files. And that's why also the language that we use in these plots is like re-execution rather than reproducibility, because we couldn't really compare to what was published. Okay, thank you.
We have one more question that's come in, which is, can you describe the code cleaning, processing, and actions needed a bit more?
Yes, so code cleaning. Okay, actually, I can even directly look into the codes where the code cleaning was. So, so what happens is that I would scan each of the files before they were re-executed. I would try to allocate fixed paths. I would try to kind of like see fixed paths and to remove them, and to so there is, for example, a function in R called base name that kind of like goes like well, yeah, and captures all this like fixed paths, and then or they would be like removed. So that's one thing. And then parsing libraries. So that was also a huge thing, because without the necessary libraries dependencies, we cannot re-execute the code. Then what was the next thing? So I was also kind of looking at how many comments people leave. So the hope is that more comments people leave in their code, the more understandable it is what they've done. So that's also something that I didn't present right here, but will be in the final stages of this analysis, the final wrap up. And then there are, yes, so for example, set directorium, that's one. And then if they're sourcing something, that's again fixed paths. So I think these are, yeah, these are kind of like the main things. Yeah. Yeah, these errors presented kind of like a low-hanging fruit. And the fact that R is not backwards compatible, there were still errors with, you know, with the libraries. So even when we used like the oldest version of R, there were errors with the libraries, and the newest version of R, errors with libraries, because every version of R has its own kind of like set of packages and errors that it works with.
Great, thank you so much, Anna. Seeing no other questions at this time, I will thank both of our presenters for their excellent presentations today. Thank you, Anna. Thank you, Qian. As a reminder, we will be sharing the slides and the the link to the YouTube video in a couple of weeks, probably, because there will be papers coming out soon that we'd like to enable to have the time that would be appropriate for them to be received. And yes, if you have any last questions, we'll probably be continuing on for a bit, but we'll stop recording. So thank you all very much for coming. Enjoy the rest of your Tuesday, and we'll see you at our next webinar in about 3 weeks' time.
Thank you all.